Yes, thank you. Hello, everyone. Today I'm going to demonstrate how we use the ICONICS tools to enhance our engineering time, reduce it quite a lot. And also at the end, we're going to talk a little bit about how we use the Azure Digital Twin to monitor wastewater and pollution from wastewater. But first, let's have a look at engineering in ICONICS GraphWorks and AssetWorks, the ICONICS Digital Twin. So what we have on the screen here is a typical pumping station, wastewater pumping station that we provide to our customers. There are some valves, some sensors, and also a pump in this. And as you can see from this monitor, where we monitor the current of the pump, we can control it manually from the user interface, or it can run in auto. We can start and stop it. And there's a lot of signals that we put into this pump. And all these signals are put into the pump based on a very specific information model that we have, both in the PLC and in the Modbus interface, and also in the AssetWorks, in the ICONICS Digital Twin that we create for it. So the current, for instance, that we look at on the graph here is one of the signals that we monitor, and you can see there are some thresholds that we use for alarming and things like that. This pump is represented in AssetWorks as an object, equipment based on an equipment class that we created. There's a lot of signals that they have different categories to them. And we use clone dynamics in the user interface quite heavily to represent the content of this object. The layout in AssetWorks is, we can think of it as a view model to GraphWorks and also to the trending and alarming system. There are quite a lot of properties related to each of the different signal types that we have. And if you look at the control module, for instance, there are some control status, function state, and operation mode. And these objects are quite common to many of the equipment that we have, like, for instance, these valves. In addition to being a view model for GraphWorks, for instance, it also acts as the connector box between our representation, graphical and alarm representations, and the point managers that we use. In this case, it's Modbus. And as you can see, there's a very strict hierarchy. Again, let's call it an information model, put into this address space that we have. So it's easy for us to find each equipment, and it's laid out precisely as we like it from the engineering tool that we have. Engineering tool, we're able to, from the engineering tool, we're able to import the entire setup based on the information models that we use in the PLC programs that we create. So the pump has all its signals defined here. And as you can see, there's also a pump 2 and 3. And what I would like to do now is to create pump number 2 in the GraphWorks display to show how we use smart symbols to do this. So this pump is the first pump that we saw, and there's a lot of information put into this, graphical elements that represent different parts of the information that we use. For instance, we have the operator status is collected, there are some coloring, lot of things going on. in order to do this the right way and make it connect with the information model that we have in AssetWorks, we use smart symbols, and we just drag these smart symbols into the drawing board as we create them, as we create a drawing. Because of the very strict information model of the pump in AssetWorks, everything is known to this symbol from the start. It's a very strict specification, and we have full control on how it's going to behave. So all we need to know is where in the asset tree this particular equipment is placed and what it's named. So having filled that in, we can save this user interface and we can go back to the live view, reload it, and there it is. Only problem is that it's not connected yet to the Modbus interface. So we saw in Workbench that we had all the information we needed in Modbus, but there's no connection in AssetWorks for this pump. So what we want to do is to instantiate one other pump in this wastewater pumping station. Obviously, this is a very simple, instantiating one equipment is a very simple task, and it's easy to imagine that we could create the entire pumping station as one class that we could instantiate the same way. But for demonstration purposes, we use a pump this time. So if we look at a pump, we can see it's based on this equipment class, and it has only 3 specific parameters that we need to fill in. I would just like to say a few words about these. The two first parameters, it's quite easy. It's the asset name and the description. They fit nicely in the first level in the equipment. The second, the third one is related to how we interact with some of the more, let's say, obscure parts of the information model with the PLC. So some of the digital flags is created or stored in one registry on a specific position, bit position. So we need this object index in order to reference this correctly. Using these 3 parameters is all we need in order to create the entire object from this library. So I just find the right class for this object, and I fill in the necessary values in these parameters and instantiate it. I do this manually now for the demonstration. Usually we use bulk asset configurator or the automation APIs for PowerShell and similar in order to do this from the engineering tool we use. Now we have a complete new asset for this pump. And we can go back to the live view and see that everything has come alive. We can click on the pump. We have access to the pump. We can start monitor the current, monitor current for both of them. So we can start and stop this pump directly. Let's start by monitoring these 2 currents from these 2 pumps, and we can start and stop this pump directly. And as you can see from this alarm, the pump 2 has already some alarm settings created. both the trend and the alarms are created as part of the digital twin configuration we do in Asset Works. So we use these built-in mechanisms for both historical data and for hyper-alarming in these classes. Because of this, we have the ability to set up the entire environment based on the information models that we have implemented in these equipment classes. Okay, so I'm going to move over to the other topic, how to connecting this ICONICS digital twin into the Azure digital twin in order to have a broader view on the world, I would say, in order to be able to monitor how this automated equipment, process equipment, acts together with other parts of the piping network, for instance. So in this case, we have a digital twin representation of an entire wastewater pipe network. There are many kinds of twins in this graph database that the digital twin really is. And we can create relationships between these different twins in all possible directions. In order to do this a little bit easier to find the right twins, I've prepared a few queries that we could look at. And let's start by finding the pumping station that we looked at. So here you can see an easier view of the pumping station that we have with the two pumps related to them. And if you look at the details, you will find some similarities between the asset structure we saw in the previous workbench picture and the properties that we have for this pump. So the pump is then put in a bigger context. So if you take a look at the entire pipeline, and now just the pipeline objects, we will see that it's a lot of different chambers and pipes and pumping stations in it. So let's see if we can find the particular pumping station that we're looking for. It should be somewhere in this area. There it is. So it's now we can see how it's related to different parts of the pumping station. It has still the two pumps connected to it. The two pumps related. In addition, there are some zones and there are some overflow chambers connected to it. The thing about overflow chambers and this entire network is that we would like to create reports that look like something like this. We want to know how much wastewater we have in an overflow chamber and where the overflow threshold is. An overflow chamber is a chamber attached to the pipe network that has the ability to let water out of the pipe if it gets too high, if the level is too high, and if it's too much water in the pipe network. The problem by doing that is that we let polluted water into the nature in creeks and rivers and similar. So we want to know how much pollution is let into the rivers and creeks. And by doing that, we would like to make a correlation between, for instance, rainwater and the level in the chambers, and also know where the thresholds for the overflow is for that particular chamber. Problem is that each chamber is different. There's not two alike chambers in the pipe network. So we need to have very specific information about this. So if we go back to the twin and have a look at one particular zone, we can have a look at how this is set up together. Let's create a flower. It looks a little bit nicer. So this is all the chambers are related to one particular zone, and we have a rainfall sensor that is also connected to this particular zone. There's not that many rainfall sensors present, but by creating relations like this, we can say that the level of the rain that falls in this area is relevant to correlate with any overflow that occurs in any of these chambers that we see here. And we can, if we go in and have a closer look on this chamber, for instance, we see that we can also have both the level and maybe even the temperature monitored for these chambers. To monitor this, we actually use IoT sensors in addition to the ordinary process automation equipment. So this is not PLC based, but IoT sensor based information that we collect. And if we take a look at the details of this, we can see that there's information modeled into this chamber that tells us where this overflow threshold is for this particular overflow chamber. So this particular view makes it possible for us to create reports like this. And as I said, the sensors, the overflow chambers will eventually let polluted water into the nature through these overflows. So we need to know which recipients of this pollution is connected to each of the different chambers. So that's also something we want to put into this model. So we created wastewater recipient models that represent a creek or a river or anything that will receive polluted water. And then we've connected them to the different chambers. So in this zone, this particular zone, there's only one such recipient, but there can be many. And again, if we take a look at this model for the chamber, we have added some information about the number of person equivalents that is related to this particular chamber. And the person equivalent is a standardized measure that can provide some information about the amount of phosphor and similar pollution that is going to find its way to this recipient whenever this chamber is in overflow. So by calculating the amount of overflow and the number of people equivalents that we have in this area, we are able to create reports that look more like this. Tell us not just whether there is an overflow or not, but how much pollution that actually is provided to this particular recipient from the different chambers. By having this, the municipality typically that owns the pipeline will be able to know which of these chambers is going to be worked at first. It's often a very costly thing to upgrade the different overflow chambers. So with that, I think I will conclude my presentation. Thank you very much for listening in.